Apparently it's 4:30, so we'll start. Welcome everybody, and first of all, thank you very much for being here instead of having dinner at this time. And my name is Walter Belgers, or in Finland it will be Valtteri, I suppose. And this talk will be about successes and failures when I did a bit of research on a particular type of lock. So I will be telling you the stories about what I tried to find out with the lock. And I think it's important to also tell what fails, because on the internet you read a lot of stuff about things that were an instant success, but of course in reality research also means failing sometimes and sometimes succeeding. It's good to be back here in Finland. I was here last time in 2015 at the wonderful T2 conference, and at that conference I opened an Abloy classic on stage, but the Abloy talk, if you went to the talk by Eden Huya yesterday, you saw him creating wonderful tools to open all the new Assa Abloy locks, but I will be talking about a completely different lock, the Miwa or Anker 3800. Miwa is a Japanese firm. They invented this lock, and it's also called Anker. That's a Dutch firm, and I'm Dutch. They sell the same cylinder that they licensed from Miwa. Now, I had a few of those in my attic, and I thought, well, that might be an interesting project to look at because they have magnets inside them. And I didn't know too much about it, and I wanted to know, how does it work, and can we defeat this lock? The fact that I had these locks in my possession was not completely strange because I am a lockpicker. I've been hacking stuff for over 25 years. It's also my profession. And I've also been president of TOOL, the open organization of lockpickers. And I'm actually currently in the process of writing a book about locksport with a few friends of mine. So to get back to the subject of this lecture, the Anker lock, and as you look inside the lock, you will see that here we have 4 pins, which are what you will find in many standard locks. Well, not so standard in Finland because you have all these nice disc detainer locks, but in other parts of Europe you will find locks that normally have pins. But apart from the pins, there's also some stuff going on up here on the top. And you can see that also the key is a bit weird. On one side of the key you have bitting, which looks like a regular key that operates the pins. But on the other side of the key you will find these 8 black blobs, and those are magnets. And actually those are 4 sets of 2 magnets, and they can also be fakes. So each blob could be a magnet or could be a fake. The magnets move sliders in the lock. So in the plug, this is the plug that needs to rotate, and you see these sliders. 2 of them move one side and 2 move the other side. And they are spring-loaded, they have a little spring, and they can move back and forth, and they move with the magnets in the key. The 4 pins are not very special. Here's an example of how that works in a lock. This is a 5-pin lock. And how that works is that the key has a bitting where the depth of the cuts match exactly the length of the pins, at least the red parts of the pins. And if these lengths match, then the pins will be exactly at the shear line, freeing up the plug, and it can rotate. Now, that's also what's happening in this lock. That's not very interesting because this is quite normal. So the interesting part, that's the magnetic sliders on the other side. And here I've shown them, so I've taken them out of the plug and put them on the key. So you can see that actually there is 4 sliders, and each slider sits on top of 2 of those blobs that can be magnets. How does this work? So here's my first success. I did something in Photoshop. It's not really very good, but it'll do. On the left depicted is a lock where there is no key inserted. And you can see that the pin here is not at the shear line. And you also see that this slider is blocking here in the plug. And this red and green thing, that's the magnet. So let's suppose green is north and red is south, then it's pointing to the left, north to the left, and it's blocking. If you insert the correct key, then first of all, the pins are being pushed down to the shear line, and also this slider, the yellow slider, is moved out of the way, so it doesn't block here anymore. And you see that in this case I've drawn a key where there's only a magnet here on the left side of the key and not on the right side. That's a fake. And you can also see that if you put a piece of magnetic paper onto the key, you can see, if you look closely, where the magnets are, and you can also tell a little bit which way they are pointing. And there's two big blobs. They are pointing either north or south, up, and the other two, they are facing left-right. Here's the plug with an incorrect key. So this key has the wrong bitting and the wrong magnets. So some pins will stick out and some sliders will stick out. That doesn't work. And with the correct key, everything perfectly aligns and it'll open. So that in a nutshell is how this lock works. Now I thought about ways to defeat the security of this lock. And when you say defeating security, you have to ask yourself, what is your threat model? I'm totally not interested in breaking the lock in any way. That's not really what lockpicking or lock sport is about. So I'm trying to open the lock without a key, but without damaging it. And we can do lockpicking or other techniques, which I will show. But another risk could be that somebody might be able to quickly copy your key if they have it in their possession for a few seconds. The first thing I looked for was, can we pick this lock with, well, then we have the four regular pins. Yes, they can be picked. They work like a standard lock. And what about the magnets? Well, you could insert a tool with a magnet on top. So you could just make a toothpick-like thing, put a magnet on top, put it in the cylinder, and move the magnets, the sliders one by one. And actually, I started my investigation already in 2019, earlier even, and I stopped for a while, and then picked it up in the COVID times because I had time. And at the time I started, there were no videos about people opening the Miwa, but meanwhile, people have done this, so it is proven that it can be picked. So the oldest videos are about 2 years old nowadays of people doing this. And sometimes they use audio amplification to make it easier to pick it. So you put a mic on the cylinder and you can hear the sliders move about. Now, I didn't pursue this at first. At first, I thought, let's see if we can do key duplication. And I took one cylinder and I opened it up. And the problem is, if you open them up, at least I cannot really assemble them correctly. But I sacrificed this one to only keep magnetic sliders on one side and the pins on the other side. So I can do my research. And to be able to copy a key, we need to know what magnets are in the key, of course. So we need some kind of device to read out the magnets, which is called a magnetometer. So I googled for a magnetometer, and I find this really nice old-school electronics schematics. And I like electronics, so I thought, let's build this. And this is the thing that I built, which is actually quite an interesting tool to take with you through the airport. So what it does is, it's very simple. You have a sensor called a Hall sensor. You put it over the magnets, and it will indicate whether it is north or south. And you see, I'm moving the sensor left and right, because some magnets are facing left-right, and some are facing up-down. And that I can determine by using this device. So I have that here. Okay, so we can read out the magnets. We can also see the bitting. So now we need to copy it. How do we do this? And here's the problem. You cannot get the blank keys. Manufacturers normally get, when they have a new lock, they get a patent. The patent is valid for maybe for 20 years. And during that time, only the manufacturer can make the blank keys. But in this case, this lock is already from the 1980s, so the patent has expired. So anybody could just make blank keys, but there is absolutely no market for it because, well, if you have the blank key, you also have to have the machinery to make the cuts, and this is quite a specialized lock. So there's nobody selling these blank keys, so they are unobtainium. So my idea was to take an existing key and just use this key and take out the existing magnets and put in different magnets. So I tried to cut away the middle part, the bitting part. So my idea was maybe we can pick the pins and use the holes to do the magnet part. Now that was a fail, because if you insert the key with just the middle slot taken out, there's not enough room for the lockpick to enter and pick the lock. Because if you insert a tool, the space is so tight that you already push down the pins too far. So that didn't work. But I thought, well, let's continue anyway. We need to do the magnets as well. So can I put new magnets in an existing key? I bought some 2x2 by 2 millimeter magnets and tried to make a setup key. So I took an existing key, took out the magnets, and as you can see, my metal working skills are not very good, and I don't have the machinery for this. So that was actually quite frustrating. This failed horribly. But I was just determined to go on, and I said, well, you know, let's suppose we are able, and we'll fix this problem in the future, let's suppose I'm able to put the magnets in the key. Then we still need to copy the bitting if we want to make a key copy. So how do we do that? And then I thought, well, what we can do is do molding. With many keys, you can just take the key, put it in a device. So this is a holder device. You put in a two-component putty, put it in there, put the key in there, and you get a mold. And then you can pour molten metal in there, and you get a copy. So yes, you can copy alloy keys, for instance. And I thought we can use this to copy the bitting. So let's suppose we have a key with the correct magnets, and now we want to copy the bitting. So I put the key that I want to bitting off in this thing, in make a mold out of it, and combine this with the existing setup key. So here I have the mold. I put in the setup key, and the mold then has the bitting. So I can pour in the metal, and what comes out is this. And I tried this on the cylinder that only has the pins on one side, and it did work on that cylinder. So the proof of concept is there. I can make a copy if I can make a magnet setup key. So where are we now? Making the magnet setup key is really frustrating because you really have to have good metal working skills. And also these magnets that I bought are 2x2 by 2 millimeter, and they are almost as thick as the key. And that makes it extremely hard to get that into the setup key. And that was actually when I stopped the project. I thought, well, for this you would really need to have a 3D printer. I didn't have access to a 3D printer. I left it. But then came COVID. And I had time. I still had a little bit of money in the bank. So I bought a 3D printer. And I continued the project. And I chose this one. This is a resin printer. You have resin printers. There are filament printers. The resin printer has a better... what do you call it? It's more precise, better resolution of what you print, and I thought that was needed for these keys. So I bought these, there's a printer and a curing station because the resin needs to cure under UV light. So it's a bit of a laborious process to print with that printer. And I thought, well, actually I had this train of thought that I wanted to have that setup key with just the magnets in there. So I started to do that. And for that I unlocked a new skill. I needed to learn CAD design, so I used OpenSCAD, the tool, and tried to duplicate the way this key looks into my CAD program. And as you can see here, I have the slit in between for picking. And this was, well, one of the first keys I actually got out of the printer. And so that went quite well. The model was not completely right, so I had to do a little bit of filing to get the key to work, but the magnets fitted in very well. And it did work on the half that only has the magnetic sliders in. So again, proof of concept, it works. Here's a later iteration where I changed my model a little bit, so now it prints keys that fit straight away. And in the meantime, I had seen those videos online of people picking the anchor lock, and from those videos I learned that the pins are first to bind, which means that if you apply tension, it will be the 4 pins that block first. And if you get them in the correct position, the lock will turn a little bit, and it's only then that the 4 sliders start to block. So you can do them in succession. First you do the 4 pins, it turns a little bit, and then you can do the 4 sliders, and then it opens. So that solves my problem that the little slit doesn't give enough room to pick the lock, because I can pick first without caring about the magnets. So I apply tension, I pick the lock coming from the side, so now I have enough room to get to the pins. And once the 4 pins are in position, I can insert my magnet setup key, push it in, while keeping it under tension, and then it should open. I tried this, it worked, so lockpicking is possible this way, but actually it was very hard. It was surprisingly hard. I thought this must be very easy. It's only 4 pins. I can pick this, but it was quite hard. The pins do have some, here on the top you can see little notches. They are anti-picking notches to make picking more difficult, but still it's only 4 pins, but yeah. But we do have an attack factor. The attack factor is that if you have temporary access to the key, you can use the magnetometer to read out the magnets. You can print up a setup key, insert the magnets, pick the lock, put in the magnets, and open it. But of course, by this time I was 3D printing keys, so you can also print, of course, the bitting. Why would I worry about all the picking stuff? So I changed my model again and included the bitting of the key. And in the model you can also type in what bitting you would like to have on the key, and it will automatically generate the correct depth of the pins, which you will see here happening here. So that's a different key. And this is an example that I printed, and that works on both sides. So I can now, with my model, make copies of keys. So that is a real attack vector. I can now, if I have temporary access to your key, I can now read out the magnets, look at the bitting, and make a copy. And the bitting, those pins, 4 pins, only have 4 different depths. So that's not much. In many locks that you will find maybe 9 positions. But since it's only 4, you can actually see the code by the naked eye. I've seen so many of these keys now that I can just see what bitting this is. I don't have to measure it. So if I have maybe 30 seconds with your key and I have my magnetometer with me, I can do the check and I can make a copy. Now the keys that I made with the resin printer did work, but I found out that the resin is very brittle. So that's a problem. First of all, if you would insert it in the lock and turn it, it could snap. And if I would drop it from here, it would also break in 2, even if it is cured well. So I needed to do something about that problem. And I thought about this, and I thought, let's go to smaller magnets. So I bought 1 by 1 by 1 millimeter magnets, but that is a total failure because they are so small, you cannot even pick them up with your tweezers without them turning all kinds of ways, and you don't know which way is up anymore, and it is just horrible. But then I talked with a colleague about this, and he said, well, you know, I have a filament printer. I can try and print a key. Let's see if that'll work. And I thought it wouldn't work because the tolerances. But he printed the key, and it actually did work. So I could have bought a standard printer to do the same things. Also an improvement is the use of disc magnets, because they take up less space. They are 2 by 1 millimeter. But that does mean, of course, that some need to go flat and some need to go on their sides. But since we're printing a key anyway, that doesn't really matter. We just print the correct hole for the magnet that goes in that position. And while we're at it, we can also leave out the holes where no magnet is needed. Remember, there are some of those magnets are fakes. So we just don't put a magnet in, and the key will be more sturdy. So that key actually works. Good, so we can copy keys. Let's make it a bit more interesting. I want to explain how the key and the cylinder match up. Because in the end, I would like to open a cylinder if I do not have the key. That's also an interesting attack. So here more of my fantastic Photoshop. And here you'll see that the sliders have magnets in them that correspond to the magnets in the key. So here you see that the magnet in the key is south facing up, and the slider has a north facing left. And it has to be that way, otherwise the slider wouldn't work. There's 5 possibilities: north to the left, north to the right, north up, north down, or no magnet. And there's also 5 corresponding possibilities for the magnet in the slider. But that means that if you have a key and you read it out, what I also should say is that the sliders, I already told you that 2 of them go one side, the other 2 go the other side, and it's always the same sliders that go the same direction. Now, if I have a key and I read out the magnets, then I know what the magnets in the cylinder must be. This is the only only possibility for the magnets in the sliders to work with this key. Because only then will the sliders go to the correct position. But of course, we can always also turn this around. If I know the magnets in the cylinder, then I know the magnets in the key, because there's a one-to-one relation there. Aha! So, if I take my magnetometer and I go to the cylinder where I don't have a key for, and I read the magnets in the cylinder, I know the magnets in the key. So that's interesting. So that's what I tried to do, but again, horrible fail, because this hole sensor is too big to fit into the keyhole. So I needed to do something about that. So what I did was I found out that there are smaller hole sensors in SOT23 packaging, and I also needed, and this should fit into the lock, and I then needed to print a PCB to put the sensor on to insert it into the cylinder. So I learned KiCad to design a very simple PCB. I bought some flexible PCB that's only 0.6 millimeters thick. And I was told by somebody that if you print your PCB design with a laser printer on inkjet paper, you can then use an iron to transfer it to the PCB, and you can etch it. So I did so, but this was also a fail. I don't know why. Maybe there are some people here that have experience with doing this, but I couldn't get it to work. But luckily, this is such a simple PCB that I could just take a Sharpie, as you can see here, and manually draw the traces. I put it in some sodium persulfate to etch it. I forgot to take this away, so I etched the complete box away, unfortunately. And I put it in a bit too long, so you can see that the traces are starting to disappear, but it was still working. And I put the little sensor there at the end, But that was a fail. Well, so it was a success for the edge, but it was a fail because that still didn't fit. So this sensor was very tiny. The PCB was very tiny, but still that was too thick to get into my cylinder. So what I did was I put the sensor not on top of the PCB, but I glued it at the end of the PCB. So that saved me 0.6 millimeters. And this was the hardest part of my whole project, to take this 0.1 millimeter wire and hand solder the device to the PCB. But it worked. So in the end, the sensor fit. I also used some epoxy, as you can see, to make sure that there is no short circuit. I tried to insert it, I tried to hook it up to my magnetometer, and it didn't work because this new sensor had different voltage levels than the old one, so I couldn't use my same magnetometer. So I thought, oh, what the heck, let's use an Arduino. I think it's a bit overkill. Arduino is like an old school 386 computer when it comes to processing power, and that's a bit much for just turning on one or two LEDs. But I built it all the same. So you see, I'm also wiggling the sensor a little bit because it's still so tight that I cannot move the sensor over the magnet to feel if it is pointing left-right. So I need to wiggle it a little bit. And that gives me the readings of the cylinder. So that was a success. And then I thought, well, since we're doing Arduino, let's make this better. So I bought a cheap shield, and I've written some code. So that's a new sensor. And with this, I can just type in what I see in the cylinder or on the key, and it will compute for me what is the corresponding magnet that goes into the key or the cylinder. All right, so the cylinder has a red-green over there, so now I know what needs to be in the key, and it depends on which slider you are looking for. And you can also, it has an SD card, so you can save the keys that you decode. And it also has an analog mode. So some old locks, the magnets are a bit hard to read. And by putting it in analog mode, it helps in identifying the correct magnets. Here you can see the check to see if the key is the same. And indeed, the key corresponds to what I have read. Great. So what can we do now? If I have temporary access to the cylinder, but I don't have the key, then I can at least read out the magnets from the cylinder, so I know exactly which magnets I should put in the key. But there is a problem, because I don't have the bitting, and I cannot really read it from the cylinder very easily. Well, what I could do is use the picking technique, pick the pins, and then use a setup key with the magnets to open it. Or I could print 256 keys, because, as I said, there's only 4 pins with 4 possibilities. So, well, depending on your thread model, that might be doable. But do we have alternatives to open a lock quickly without using lock picking, single pin picking? Yes, we do. There is a technique called bumping, where you have a key that is cut deep enough for the pins to go all the way down. But these little teeth in between the cuttings, they are high enough to touch the pins. And when you smash on it, then it's Newton's law. The energy gets transferred, and the pins will separate for a fraction of a moment. And in that time, you can open the cylinder. So I tried that. These resin-printed keys, if you would bump them, they would break in a million pieces. But I tried it with the plastic keys, and that works. So, of course, I need to have the correct magnets in there. So I need to print a bump key matching the magnets in the cylinder. And of course, I took the video where it works in one go. Normally, it will take maybe 5 or 6 bumps, but it's not too bad. It does work quite nicely. And here you can see, so it has the incorrect bitting, but these teeth are still high enough to touch the pins. So that works. Now, what else can we do to get a lock opened, not using picking and not using a bump key, there is another method, which is impressioning. And this is really a cool technique. We also have competitions in impressioning at Tool or at in Locksport. And it means that you wiggle the key, and if you take a blank key, so all the bitting is at the highest position, you wiggle it in the lock, and then the pins that are too high up will push into the key. And if you take a key that's made out of brass, that is soft enough to leave visible traces, and you use a magnifying glass, you see the traces, you file a little bit of material away until you get the key. So this is a picture I made at the French Championships in 2019, I think, where I filed the key, so you can see my filing. And yeah, it looks a bit weird because I file straight over the key, but it doesn't really matter what I file away from the key as long as the place where the pin goes down, it goes to the correct position. Now, can we do the same thing with the anchor lock? Well, we need to have a material that is like brass. And these pictures show aluminium, which was for another test that I did, for the bumping test, but these are the only pictures I have of the fabrication of it. This was done by this colleague of mine who had a little CNC machine at home. And here he CNC'd a metal key from the CAD model. And here is a brass key that I used for impressioning. So this key has all the bitting at the highest level. You put it in the lock, you wiggle it, you get tiny markings that you can see there with a red circle. And there you file away a little bit of material, and you try again and again and again until you end up with the correct key. It did work. But again, just as with the lockpicking, it was very, very hard. And I have no idea really what makes it so hard in this lock, because I didn't find anything that would defeat impressioning. But matter of the fact is, this was quite hard to do. But the attack factor at this moment is that if we have access to the cylinder, but not the key, we can read out the magnets, and then we can create a setup key and bump for one-time opening. So I think that's quite feasible. The bumping works well enough for this to work. Or we can do impressioning, but I don't think that's a real live attack because it's just too hard. Now let's make it a little bit more interesting. These locks were sold, or are still sold, as high security locks, and they are quite expensive. They cost maybe 300 euros per cylinder. So it's not really used by end users. Where you will find these locks is in large facilities like big companies or hospitals or whatever. And those will normally want to use them in a master keyed system. Which means, master keying in general means that you have a bunch of cylinders and they all have their own key, which also are called user keys, that will only operate on that one cylinder. And then there's also a key that operates on multiple cylinders. So you can have different levels. So this key is a key that operates these 3 cylinders, and this key operates those 3 cylinders, and then you can even have another key that operates on all 6. And yeah, you have multiple levels in this system, a whole hierarchy. But to explain how this works in a simple system, let's focus on 2 individual cylinders with an individual user key and 1 master key. And I'll show you how this works for a generic pin tumbler first. Now we have 2 users, Alice and Andy, and they have their own lock, their own cylinder. So Alice has a cylinder, Andy has a cylinder, and Alice tries her key on both cylinders. And as you can see, it works on this lock because all the pins are at the shear line. But it doesn't work in Andy's lock because the second and last pin are still blocking. And you now also see how master keying is implemented in these locks. You take the pin stack and you just cut the pin in half once more. And then you get 2 positions where the pin may sit for it to open. So you can create 2 keys that will work. And one is the user key and the other is the master key. So this is the key of Alice that only works on Alice's lock. Then of course Andy also has a key. And you will see here that this key will work on Andy's lock on the top right, but it will not work on Alice's lock because again the second and fifth pin are blocking. And then we can create a master key that will operate both cylinders. Now, there's also a code there. That's the bitting code. So the higher the number, the deeper the cut. And if we take Alice and Andy's keys and the master key, you will see that they only differ in 2 positions. And you will also see that the master key has more material in those places than the user keys. And that is for a reason. The reason is that you don't want the user, you don't want Alice or Andy to just file away a little bit from their key and suddenly get a master key. You cannot just file material on top of there. So if you want to have the master key, you need to buy a blank key. And the idea is that if you have a good system, you cannot just easily buy a blank key. So that's an extra security measure. It also means that the way to defeat master keying is the following. Suppose you are Alice and you are at work and you have your own office and you have your own lock. Your key works on the lock and you have the code of your own key. What you can do is you can print keys that differ in 1 position. So the first position is a cut 3. You print 2 keys with positions 1 and 2. And you can try them both out in your own cylinder and see which one works. And maybe none of these work. Okay, and then you do the same for the second cut. So you have a cut 6, so you try 1, 2, 3, 4, 5. We don't need to go deeper because the master key is higher up. You try them all out and you will find maybe that 1 key works. So that gives you information. And you go on for the 3rd, the 4th, and the 5th. So you can do that in sequence. Because you start with a working key, you can vary only 1 pin at a time, check all the different heights, and this will give you information of possible other bittings. And then you know that the master key is like this, because you take the 4 cut there, you take the 1 cut there, and you have the master key. So master keying gives you more functionality, but at the cost of security. And actually, if you know that there is only 1 master key, only 1 other key that will fit on your lock, you don't even have to bother trying out these keys because you already had the different cut. But what about this anchor lock? Because in here we have magnets. And yes, they can also be used for master keying. So that's the reason why these sliders can have 2 magnets and why we have magnet pairs. Right, so here you see a slider and there are 2 spots where a magnet can be. How does this work in practice? Well, suppose I am a user, I have my own key to my own office, and I can read out the magnets from my own key. They are printed there. And I already know what needs to be in the cylinder so it works with my key, right? Because there's a 1-to-1 mapping. So to have this key work, I know that these green magnets must be in the cylinder. Now, let's find out what the master key looks like. Yeah. I have read the magnets from the key, but next what I'll do is read the magnets using the small magnetometer from my cylinder and see what's in there. Of course, the green ones are in there, but I might find some other stuff as well. So by reading out the cylinder, I find out that there is 2 more magnets. So what does that tell me? Now, the master key will have to have magnets to operate each slider. Each slider needs to be moved to the correct position. So these middle 2 sliders, they only have 1 magnet. So the master key must have these magnets. Otherwise, that lock would not open. Now, the blue magnets, they are in this cylinder for a reason. So if my key does not operate the blue magnets, and there is one other key that does, the master key, then yeah, it's the master key that operates those blue magnets. So I know for sure that these magnets will be in the master key. Now, what to do with the sliders with 2 magnets? Should we put the other magnet in as well, or shouldn't we? We shouldn't. Let me show you why. Suppose this is still my cylinder and my key. Now I have a neighbor, key B, a neighboring office, and they have their own cylinder. And as you can see, that cylinder is a little bit different. And you can also see that key A does not work on cylinder B, and vice versa. And the reason is that we have here there. Bottom right is a south, and here bottom right is a north. And so this key has bottom right and north south, and this one has south north, so they are not interchangeable. Now if I go to my neighbor's door and I read out the magnets in that door, then I learn something new. I learn that, the neighbor has a north and I have a south. So I know that here is no magnet. Can't be. What about the one here on top? I don't know. The neighbor has the same magnet as my door, so I just don't know. I only know that if there is a magnet there, it's a north-south. But otherwise, I need more information. I need to go to more doors to read them out. And then there's 2 spots left. And yeah, one I don't know, because I haven't seen any lock with a magnet there. And the last one, yeah, I don't know. It could be south-north, because in the neighbor's door I saw a magnet there. So yeah, it could be south-north, nothing else, or it could be nothing. But by going to more and more and more doors, the more and more I will learn, and the better my master key will be. The problem is, though, that they do not just do master keying in the magnets, but also in the pins. So that works like a generic master key system. So you have pins in different lengths. So these are the pins 1, 2, 3, 4 deep. And you have spacers 1, 2, and 3 that you can combine with the pins to get multiple shear lines. And in this example, we see that it's now lying flat. There is one pin that has a spacer in it. So this is from a master key system. But the issue is that this whole story about we can go deeper and check cut by cut to see which one is higher, that doesn't really work anymore, because we also have the magnets. Which means if I have the key, I could maybe file it down so the bitting is that of the master key, but it wouldn't work because maybe the magnets are different. So the manufacturer does not have to take into account that all the bitting needs to be higher than lower than that of the master key. So that trick doesn't work. So how does it work then in practice? So to show you, I got from a friend a bunch of old cylinders, 5 of them, that came from an organization in the Netherlands that replaced their locks. And these were master keyed, but I did not have any key to them. So what did I do? I made a schematic, and I'm trying to figure out the setup of all 5 keys and all 5 cylinders. Step 1, I have no keys. The only thing I can do is measure magnets. So I took my magnetometer and I measured all the magnets in all 5 of the cylinders and put them in here. And you can see already that the middle 2 sliders, they have the same magnets everywhere in all the locks. And only the bottom and top slider, they are different for each lock. So using that information, I can figure out what the master key looks like. These are the magnets in the key, in the master key. And I know this because the master key cannot have the top left magnet because it is RG here and GR there, green, red, and red, green. So by using the magnets there on the top right, I know that those magnets will work on all 5 cylinders. That also means by knowing that, I can figure out what the magnets are in the individual user keys, because the user keys must differ as much as possible from the master key. In other words, if there is a magnet in the cylinder that is not used by the master key, it must be there for a reason, the reason being that the user key, individual user key must use it. So by taking the master key and the magnets in all the cylinders, I can figure out exactly the magnets of all the individual keys. So those are the ones that differ most from the master key and still operate these cylinders. And now comes the hard part. I need to know the bitting, and I don't have a key to start with. If you have a key to start with, it's much more easy, but I didn't. But luckily, of these 5 cylinders, one was a half cylinder, number 5. And what I did was I used a bump key with the magnets that I found out to bump open this cylinder. And why did I open this one? Because the half cylinder I can disassemble and reassemble for it to work again. And I can't do that with the with the cylinder that has 2 sides. I cannot get them back together. But with a half cylinder I can, so I was lucky to have a half cylinder in there. And then you can open it up and you can just look at all the pins that are coming out. And you know exactly what the correct bittings are in this lock. And I can see that there are 3 pins that have 2 possibilities. So that means that there are 2 times 2 times 2 is 8 possibilities for the master key bitting. Well, 8 is doable, so you just print 8 keys with all the correct magnets and try them out in all the cylinders. And then I found out that only the combination listed here would open all cylinders. So I know that's the master key. I'm already done actually, because I have the master key to open all the cylinders, but I'd also like to know what all the individual user keys are. So I'm using this master key trick again. What I do is I have on top you see the real master key bitting, and so I know that this key will work on all cylinders, and then I'm going to vary each pin individually to all different depths and try them out in all the different cylinders and see which one works. And with that I can decode exactly all the bittings in all the cylinders. And what I actually did was I printed only 4 keys, tested them all out, wrote down the results, filed away the bitting to the next, tried them out. And with these 12 keys, I was able to get all the different bittings in all the different cylinders. Again, these bittings are in the cylinder for a reason. So if I find a possible bitting that works on the cylinder but is not in the master key, it must be there for a reason. Reason being, it is used by the user key. So knowing the master key and all the bittings, I can figure out what the keys are, the individual keys. I then printed them, and of course they all nicely work. And I now also have the master key that of course is gold. Yeah, there it goes. And the fun thing is I can now even create keys that work on a specific subset of cylinders. Not all permutations are possible, but I can make those as well. So for the master key, to get to the master key, you will need, this is the difficult part, you will need 1 key to start off with. Because then you can change the bitting per pin. So if you work at a place where you have 1 key and you know which cylinder it is in, you can start and do the attack. By decoding all the bittings, you have a limited set of possible master key bittings, depending on how many cuts. Maybe it's 2, maybe it's 8. 8 as in my example. Theoretically, it could go up to 81. And then you go to other cylinders and try out which keys still work. And if you have 8 keys and 4 no longer work, there's 4 left that can be the possible master key combination. And if you go to a new cylinder, you will learn more, and maybe then only 2 will work, throw away 2, and the remaining 2, one of them is the correct one. So it is a matter of going to more and more cylinders. And with each one you see, you get more information about getting the master key. It is still quite a bit of work. More work than with a regular old system. But I think it's quite doable if you're a bit handy and have a 3D printer. So to summarize, and let's make this a bit visual. We start, the question is, do we have a key? If you have the key, it's now easy to measure the magnets, decode the bitting by the naked eye, put it in the CAD model, print the key, and it'll work. So we can copy a key. And the fun thing is that if you do not, if you see a picture of a key, oh, well, I'll explain it later. First, let me do this. So if you have a key, you can make a copy. If you don't have the key, we have a few possibilities. First of all, we can decode the magnets because we can read them out from the cylinder. But then we need to open the lock. So we need the bitting. What you can do is make a setup key and pick the lock. But I've made it light blue because that's quite hard. You can do impressioning. That's also quite hard, but the advantage is that it will end up with giving you a correct working key. You can try 256 different keys, and one will work. That will also give you a working key. Or you can bump, which is quite easy to do, and open the lock once. And only if you are able to disassemble it, then you can look at the insides and also get the bitting and get a working key. If that is then master keyed, then what you can do is decode all the possible bittings in your cylinder by using 12 keys. And then you can do, by process of elimination, you can go to the next cylinder, the next one, and each time you measure the magnets, find out more information, and narrow down what the master key will look like. And you're happy. So, conclusion. I think this cylinder is still quite interesting. It still requires some work to get it open, and it's fairly pick resistant. But of course, with 3D printers nowadays, yeah, it becomes, well, not to say very easy, but quite easy to make a duplicate of a key. And this is a problem that all the manufacturers face. So also the alloys, if you have a picture of that, you could make a duplicate key. It is still non-trivial for the magnet. So if you have a picture of the key, yeah, you don't know where the magnets are, which one are fakes, which one are magnets, and which position they have. But of course, yeah, if you know which cylinder the key works on, you can just go to the cylinder and read out the magnets from the cylinder instead of the key, and then you also have that information. So that's an issue. Companies are trying to prevent 3D copying of printing keys. And yeah, one of the things that they are doing also for patent reasons is put all kinds of movable elements into the key that are hard to print. You cannot really easily print something that moves within the key. Although there are also ways to defeat this. There was a nice talk last year about this. So conclusion, finding the ground master key still requires quite a bit of work. It's not like you're done in 10 minutes, more than with conventional locks, but it certainly is doable. And my last advice is to only do testing on your own cylinders, as we do in Locksport. I mean, I've had these keys break in my own cylinders, and then I had to, I could no longer use my cylinder because the key was stuck inside, couldn't get it out. So don't try that on cylinders that are really in use. I would also like to thank my colleague Guido, who did the CNC work, but also Ankerslot, because that's a Dutch company that builds these cylinders in the Netherlands, licensed by MIWA. And I contacted them before I did a presentation about the log, saying, well, I've been doing some research. Maybe it would be good to talk with you and see what you think about this, and if there is stuff that I cannot really disclose. And they said, oh, sure, come on over. So I went to their factory. I got a nice walk through the factory. They showed me everything. They only have one head developer. And that was really cool. They even gave me some unobtainium blank keys. So I can now do bumping with the original anchor key with the anchor magnet. And of course, they knew that these techniques are possible. It's also not a cylinder that is being actively worked on to get it redesigned. Anker has other logs that they work on. And I'll end by thanking you again for spending your time with me today, and keep on hacking.